Welcome to the last lesson for this section of Pre-Calculus 12. So today we're going to be looking at the sum of two angles, the difference of two angles, even and odd cofunction identities, phase shift identities, and double angle identities. So we're just going to throw a whole bunch more identities into the mix and then look at a few ways that these can be used. Generally, as with all of our other identities, sometimes you just have to play around with them a little bit before you figure out what it is you're looking for. So let's start with the sum of two angles. On your formula sheet, just so that you can use them for your workbook problems, there are tangent. We do have tangent of two angles as well, but we're really only going to be testing you on sine and cosine of two, the sum and difference of angles with sine and cosine. So the sum of two angles. So when we're adding angles inside a trigonometric function, it is definitely going to change the value of that function. And so we can see that there is a particular relationship. So we have sine of a plus b, both inside the function, two angles added together, is equal to sine a cos b plus cos a sine b. It's not just equal to sine of a plus sine of b. It doesn't break up like that. It's stuck inside the function. Cosine of a plus b equals cosine a cosine b minus sine a sine b. We also have a formula for the difference of two angles. We have that inside, so sine of a minus b equals sine a cos b minus cos a sine b, and the cosine of a minus b equals cosine a cosine b plus sine a sine b. So similar, again, these are on your formula sheet. You don't necessarily have to memorize them. So another one that's good to remember, these are what we call even odd identities. Okay? So we have sine of minus a equals negative sine of a. Okay, so if you're taking sine of a negative angle, and you can see that if you look here. So if this is a, this is minus a. Okay, and similarly, if we think about sine, cosine, and tangent of this angle, cosine of minus a is actually just equal to cosine of a. And since sine of a is equal to minus sine a, cosine of minus a is equal to cosine a, tan of minus a equals sine of minus a over cosine of minus a, which is negative sine of a over positive cos of a, which is equal to negative tan of a. So, and as if you plan to go on to calculus, this is because one of the reasons we can consider these is that cosine is an even function, so it's symmetrical about the y-axis, and sine is an odd function, which means it has rotational symmetry around the point 0, 0. So, we also have what we call the cofunction identities. And that's just for sine and cosine. So this is just recognizing that sine of pi over 2 minus a equals cosine of a. And there's a whole bunch of different identities and different ways we can record the phase shift. So if you think about what it looks like here, if you have your and we don't necessarily have to have all of these, but this is your cosine of x, okay, and this is your sine of x. So you can think about how these may have been transformed from each other. Okay, so if you take, for example, sine of a is equal to, so if we have a sine here, is equal to cosine of A. So if we want to change from cosine to a sine graph, we could take our cosine and move it A minus pi over 2. Okay, so these are some of our lovely cofunction identities. So we have our double angle identities as well. And these are actually special cases of your sum of two angles identities, which you get when you use, if you make A and B the same in your sum of two angles formula. So sine of 2A equals 2 sine A cosine A. Cosine of 2A is equal to cosine squared of A minus sine squared of A. But this can also be manipulated in a couple of ways. So remember our Pythagorean identity. We have sine squared A plus cos squared A equals 1. So I can replace cosine squared with 1 minus sine squared, and I can replace sine squared with 1 minus cosine squared, which gives us the following. So we have 1 minus 2 sine squared A, and that's also equal to 2 cosine squared A minus 1. Okay, so you can just start with the first one, but you can rearrange it in a few different ways. Okay, so similarly, we might be, and if you need to look up there, the tan formulas are found inside your books. Okay, so one way we can use this is we can find sine of 5 pi over 12 without using a calculator. How on earth do we do that? Well, 5 pi over 12, what I know is I know my special triangle angles. So what triangle angles do I know? I know pi over 6, I know pi over 4, I know pi over 3, and I know pi over 2. So these are all special angles. So what I might notice is if I rewrite these over 12, this is 2 pi over 12, this is 3 pi over 12, this is 4 pi over 12. So if I wanted to find the sine of 5 pi over 12, I can get 5 pi over 12 by adding 2 pi over 12 and 3 pi over 12. So sine of 5 pi over 12 is equal to the sine of pi over 6 plus pi over 4, which I discovered by writing all those things over 12. So now what I can do is I can use my sum of two angles formula. So I know that sine of bracket A plus B is equal to sine A cos B plus cos A sine B. So I'm going to let my pi over 6 be A and my pi over 4 be B. So now I'm going to write sine of 5 pi over 12 is going to be equal to sine of pi over 6 cosine pi over 4 plus cosine of pi over 6 sine pi over 4. Okay, so I've done my substitution properly, so now I can use my knowledge of special triangles. So sine pi over 6 is the short one, which is 1/2. Cosine of pi over 4 is root 2 over 2, plus cosine of pi over 6. So what is cosine of pi over 6? Cosine of pi over 6 is the long one, so that's root 3 over 2. Sine pi over 4 is root 2 over 2. Okay, and it's all in quadrant 1, so everything is positive. So that's going to give me root 2 over 4 plus root 6 over 4, which is equal to root 2 plus root 6 over 4. And that's my final answer. It's got a rationalized denominator, and I can't simplify that sum anymore. Okay, what else can we do? We can actually sometimes simplify things by going the other way. So sometimes we're given something that is expanded using sum of two angles, and we can simplify it to just a sine or cosine of a of the actual sum of those angles. So let's see, we have sine of pi over 6 minus x, cosine pi over 6 plus x, plus cosine of pi over 6 minus x, sine of pi over 6 plus x. Okay, so being realistic, I do understand that somebody might see this and then their initial instinct is to scream or cry or try to run away. But I really prefer you don't do any of those things and take just a moment and see if you can recognize anything in common. These two are the same, so I'm going to call them A. And this one are the same, so I'm going to call them B. And if I go back and I look at my formula sheet, I notice that this is sine A cosine B plus cosine A sine B. That's actually exactly the same formula I just used. So this is sine A cos B plus cos A sine B, because we're going to let pi over 6 minus x be A and pi over 6 plus x be B. Okay, so what I know is that this is equal to the sine of A plus B. We're going backwards of the way that we did in the other problem. So what is A plus B? This is sine of pi over 6 minus x plus, and then this is all inside our sine function, pi over 6 plus x. And what do you know? Minus x and plus x cancel. This is equal to sine of pi over 6 plus pi over 6. So this is equal to sine of 2 pi over 6, which equals sine of pi over 3. And ultimately, that is equal to root 3 over 2 because it's the long one on my 30, 60, 90 right triangle. Okay, what else might we have to do with these identities? So we might have to solve an equation. So let's say we have radical 2 sine 2x minus 2 sine x equals 0. So generally, if I have a double angle, I'm going to want to get rid of that double angle because I want to solve, I don't want a 2 inside multiplying unless it's multiplying everywhere. And in this case, it's only multiplying one of those. So I'm going to try expanding. So I have radical 2 sine times 2 sine x cos x, because that's my sine of double angle, minus 2 sine x equals 0. Okay, so now I'm going to factor out a 2 sine x. So I get 2 sine x, 2x. Okay, so 2 sine x times radical 2 cos x minus 1 equals 0. So I have two options, either 2 sine x equals 0, so I get 2 sine x equals 0, or I get radical 2 cos x minus 1 equals 0. So here on this side, I get cos x equals 1 over radical 2, and if that is my x and that's my r, I can pretty well tell this is a 1 radical 2, 45, 45, 90, or a pi over 4 right triangle. So x, if I'm looking here, is pi over 4. Because I haven't been told, I need to look for which solutions I'm looking for. I need to look for my two solutions here. So this is a positive cosine. My other positive cosine is going to be pi over 4 down here. So it's going to be 7 pi over 4. If I'm not told exactly which solutions, I have to write the general solution. So I'll do that in a minute once I solve the left-hand side. So I know here sine x is going to be 0. So in between 0 and 2 pi, I have x equals 0 and x also equals pi because those are my two zeros. So now I can do my general solution. If you're not asked for what kind of solution, it is a general solution. And the general solution is going to be, we have x equals 0, or we don't even need to write the 0, we can just write pi k. Okay. We have pi over 4 plus 2 pi k. and we have 7 pi over 4 plus 2 pi k. And those are my 3 solutions. And for all of them, k is an integer. And so ultimately, with these new identities, just like with any of your identities, you don't have to memorize them because you have a formula sheet. However, while you don't have to have them exactly perfectly memorized, you do need to have a reasonable idea of what they look like so that when you're trying to pick them out of a mass of math, you can say, oh, that looks like it might be a sum of 2 angles, so you know which area to look at. Because a lot of this is just about replacing things with other things they're equal to make your life easier.